Assalamu alaikum. In network performance evaluation studies, we're often interested in seeing how two variables are associated together or how are they related. And then using this information or exploiting this information about association between two variables, we're interested in making predictions. So if we know one variable and we know that an association exists between that variable and another variable, then we can make a model in which we can make predictions about how that variable would be affected. So today we're going to talk of mathematical notions of correlation and regression to talk about these issues. So the first thing I want to talk about is correlation, which captures our intuitive understanding of how two variables are related together or how are they associated. Up till now in this course, we have only talked about a single variable. We've talked about using descriptive statistics to summarize information about a single variable. We've also talked about estimating the general properties of a population while knowing a sample about a single variable. So such statistics is known as univariate statistics. But often in practice, we are interested in seeing how two variables or more than two variables are associated together, because a basic way we understand the world is in the form of cause and effect. So we want to establish that doing this would cause this to happen. While this is commonplace in our everyday thinking, but in formal statistics, establishing causal relationship is not trivial. And in fact, in most observational studies, all we can say is that two variables are associated together. But we cannot establish for certain that one variable is causing the other variable. Furthermore, our intuitive notion of correlation fails us sometimes because, like any mathematical abstraction, correlation is defined in a specific narrow sense in which we are trying to capture the association between two variables. So in most of the cases, this is a good approximation. But we'd be seeing that when the relationship is non-linear, correlation may not be a very good indication of how two things are related, and it may give a misleading statistic. So when we want to observe how two variables are associated, we are interested in seeing how these two variables move in step. In other words, if we increase one variable, does it also cause an increase in the other variable? If it happens so, we say that they are positively correlated, which means increase in one variable causes a corresponding increase in the other variable. So this then specifies the direction of the correlation. We can also have a correlation in the opposite direction, that increasing something decreases the other variable. So correlation then is specified in terms of direction. It is also specified in terms of the strength of the association. If the change in one variable always produces or almost always produces a corresponding change in the other variable, we'd be saying that this association is strong. But this association may also be weak when the correspondence or the moving in step of the two variables is not very strict. So let's talk about these two issues of the direction of the correlation and the strength of the correlation in some more detail. Initially, we'd be talking about the direction of the correlation. So as you can see in the slide now, you see that you can have a positive correlation or a negative correlation. And in a positive correlation, the scatter plot of the two variables, in which a scatter plot is a graph in which a single point is a pair of variables in which the two variables that are associated are paired together. So you would have an x variable and a y variable, and you have many of these points and you plot all of these on the graphs. So if you have a graph in which the slope of the line which is connecting these dots or the line all the dots are very close to, if this line has a slope that moves upward as we go towards right, we would say that we have a positive correlation. In more intuitive terms, what this establishes is that the increase in the x variable produces also an increase in the y variable. But if you have a negative correlation, the slope of the line would actually be going downwards as it moves towards the right hand side. So this is known as a negative correlation. Intuitively, this means that increase in the x variable is producing a corresponding decrease in the y variable. When you have a perfect correlation, all of the points actually line up and come on a line. So as you can see, the positive correlation, all the points are actually coming on a line, and the slope of this line is going up as it moves towards the right hand side. For the negative correlation, if you have a perfect correlation, all the points would actually be on a line, and the slope of this line would be going downwards. So we've talked about the direction of the correlation. We're also interested in seeing how much they are associated, or the strength of their association. In that sense, we would classify the correlation either as a strong correlation or a weak correlation. So this is fairly arbitrary. Strong, there is no single point beyond which you would say that this is a strong correlation and this is a weak correlation. But generally speaking, if the individual dots are very close to the line, or the diffusion of the points on either sides of the line, which is acting as the model of this scatter plot, if you have lesser diffusion, we would say we have a stronger correlation. And if you have a lot of diffusion, and knowing one value, you do not have any idea about the other variable. In other words, you have a big spread of data. This would be a weak correlation. So when we're measuring correlation in the mathematical sense, we define a measure, and typically we use the Pearson correlation coefficient, which is a measure which ranges in the value range of -1 to 1, where perfect correlations have absolute correlation coefficient values of 1. So a +1 value would mean a perfect positive correlation, and a -1 value would mean a perfect negative correlation. So a value of +1 and -1, or values close to it, show strong associations. If you have a value close to 0, then you have very weak association. And amongst this range, you have a range of values from strong associations to low associations. So we can see a range of correlation values. You can see a lot of graphs in this slide. In the left-hand side, you see the top graph is a correlation of 0, which means you can see a diffusion of dots, and there is no definite pattern. You don't see the dots lining up in a specific direction. So a correlation of 0 would actually mean that the two variables are not associated. So it can be something you can imagine, for example, the height of some person and his job satisfaction, or the performance on job. There is no apparent correlation between these two variables, and one would anticipate that if you were to get measurements of both these variables, you would see that they would be all over the place. So you don't have a definite pattern. It's not as if someone who is tall, he also performs well in his job, or vice versa. So this would be correlation of 0, which means there is no correlation. A positive correlation, you have many physical phenomena, for example, you have the theory of Hooke's law, in which we are actually estimating the stretching of a spring as weight is applied to it. So what you have is that if more weight is applied, the stretch is more, and if you remove the weight, the thing goes back. So you would have a perfect correlation. You increase the weight, you have increased stretching, and if you remove the weight for smaller values, you have smaller stretch. So this would be almost a perfect correlation. in statistics, it's very hard to find a correlation of +1 or -1 because that would mean a deterministic function. Everything is lining up perfectly on a line. In a statistical sense, the values almost always have errors associated with them. So these may be measurement errors or these may be random variations. So you have a systematic relationship and then you also have some random variation. So even if you have a very strong correspondence, it's very rare to find a correlation of 1. So let's have an example of moderate negative correlation. So one can imagine the correlation between one's age and the ability to play sports. Typically, as the age increases, the ability to play sport actually deteriorates. So that would mean that you have a negative correlation, but you always have special cases in which someone who is aged, he may be good in sports better than someone who is having lesser age. So this is a statistical relationship, not a deterministic relationship. So correlation is a good measure, and so we have to interpret the correlation measures in light of these thoughts. So let's now talk about how can we relate variables when they actually have different spreads, because we've talked of the intuitive notion that an increase in some variable produces a corresponding increase in the other variable. But it may be that these variables are measured in completely different units. So the spread of one variable may be very less, and the spread in the other variable may be very large. So how do we correspond the amount of changes in these two variables? So the way this is done is actually by standardizing both variables. And we've talked about z-scores, and z-scores are just the number of standard deviations above the mean. So that actually is an objective measure that informs us with respect to the variation in that variable, how far away is the change. So if you have in one variable you're increasing the value by, let's say, 1 standard deviation above the mean, do you also get a corresponding increase in the other variable? If an increase of 1 standard deviation above the mean in one variable produces a corresponding change also of 1 standard deviation above mean on the other variable, we would have a perfect correlation. And if that is not the case, you have weaker correlation, and the amount of correlation would depend on the relative ratios of these z-scores. You can see 4 quadrants in this graph. The center point is the point of the mean of both the variables. And on the left-hand side of the x-axis, you have values that are less than the mean. On the right-hand side, you have values that are higher than the mean. And similarly for the y-axis. So if we take the product of both z-scores, it would be a positive value if we are in the first quadrant, which is the top right side. It would also be positive if we are in the third quadrant, which is the bottom left side. For the other 2 quadrants, we'd be having negative values. So if most of your values are in the first and third quadrant, we would say that we have positive correlation. And if most of the values are in the second and the fourth quadrant, we would have negative correlation. So we can see here that for a positive association, the cross products would be mostly positive, and we'd be seeing the significance of these cross products. Cross product का यहाँ मतलब ये है कि the z value of the x variable multiplied by z value for the y variable, and it just means कि दोनों variables जो हैं वो mean से कितना ऊपर है. So अगर एक variable mean से ऊपर है, दूसरा mean से नीचे है, तो इनका क्रॉस प्रोडक्ट नेगेटिव होगा. लेकिन अगर दोनों वेरिएबल्स मीन से ऊपर हैं या दोनों मीन से नीचे हैं, then you would have a positive cross product. So we can see all these variations in the slide now. So let's now see how we actually calculate the formula for calculating the correlation coefficient. And this coefficient is due to Carl Pearson, who discovered it in early 20th century. And the idea is very simple, and it can be expressed in many different interpretations. In fact, there is a paper which has given 13 different interpretations of it. So I've chosen a very simple interpretation of it, and it's just the average cross product of the z-scores of the two variable, and that can be seen in the slide here. So you are multiplying the z-score for the x variable with the z-score of the y variable, and you're doing this for all your pairs, and you add it up and then you take an average of it. So if you see, the denominator has n minus 1, so it's a special kind of an average, and we've already seen this when we talked of estimating from a sample. So if we are estimating from a sample, and this is by the way the sample correlation coefficient, so we would then have n minus 1 in the denominator. We've seen this before, that if you want to estimate the average of a population when having n degrees of freedom, in other words, you have n items and you're trying to take an average, you would be dividing by n minus 1. So that's the reason we have n minus 1 here. You can also see in the slide the formulas for the sample standard deviation for x and the sample standard deviation for y. And in both of these cases, you have n minus 1 in the denominator. Also, the letter that is specific, that is used for specifying the Pearson correlation coefficient when we're talking of the samples, is the letter R. And if we are talking of the population correlation coefficient, we'd be using the letter rho, the Greek letter. This is consistent with our terminology, and we're using the Greek letters for population parameters. Let us now study an example to clarify the idea we've just discussed, and to see how this formula for calculating the correlation coefficient can be applied. So we have in the slide a table in which we have two variables. The first variable is throughput in kilobits per second, and the second variable is round trip delay. And we want to see if these two variables are related or associated in some way. So we would also be interested in seeing if they are positively associated or negatively associated, and the way to determine that is to find out the Pearson correlation coefficient for this. So for doing that, we'd be first of all listing all of this information given in the table in another table, through which we'd be calculating the different parameters necessary for calculating the Pearson correlation coefficient. So that table is now given on the slide, and you can see the various x values and the corresponding y values. So we determine first of all the mean and the standard deviation for x and y, and represent it by x bar and sx and y bar and sy respectively. So we get a value of 58.67 for x bar, and y bar is 756.67, and the standard deviations are also shown. So how do we proceed from here then? So we have to first of all convert the x values and the y values into z-scores. So you can see those values listed in the table now. So if we calculate the mean of the z-score, if we calculate the mean of all the z-score, it has to be 0 and the variance has to be 1. So you should be checking that for both z of x and z of y. And then we can now apply the correlation coefficient formula, which is just the sum of the products of zx and zy for all your sample items. So if we take the sum, we get a value of minus 6.60. And because the correlation coefficient is the average value of this sum, we divide it by 8, which gives us a value of minus 0.82. So because we have a value of minus 0.82, it tells us two things. Firstly, it tells us the direction of association. We have negative correlation, which means that the variables throughput and the delay variable, they are both negatively correlated. Increase in one causes decrease in the other. So we have to be careful when we say causes, because association does not actually show causal relationship. But what we can say is that of all the pairs that we had, usually the higher value on one variable coincided with lower values on the other variable. We'll be shortly talking about the dangers of inferring causal statements from correlation data. But generally speaking, we have a negative correlation. The other aspect is that this correlation is quite strong. You have a value of minus 0.82, where 0.82 is indicating that most of the values are actually quite close to the line which is our model of the common trend. And we'd be seeing that this line is actually the regression line, which we'd be covering in the second part of this session. So now we can talk of some caveats of the correlation measure, in which we're talking of the problems with using this correlation coefficient. The first problem I want to talk about is that correlation coefficient measures linear association. So typically what it assumes is that you would have a line-like function which is modeling the association. So you have a monotonic increase or a decrease. But if you have a non-linear function, which is which is the function of association between these two variables, then correlation coefficient would not be a very good measure. So if you see the slide now, you would see that the two variables are associated in a sense because they have a non-linear pattern. So the pattern is evident. And we would say, intuitively speaking, that they are closely correlated. But our mathematical definition of correlation, since it only measures linear association, is going to give us a very small value, because in this case, in some cases, increase in one variable is causing or is associated with decrease in the other variable, and also vice versa. So eventually, if you average it out, you would have a value close to 0. The cross products most of them would cancel each other. And because of that, the correlation coefficient for this is very small. This is minus 0.009, which is a very small value, which is betraying our intuition. So we have to be very careful that we are only applying correlation coefficient as we've defined only for linear data, because the interpretation of this coefficient for nonlinear data may be misleading. Let's now talk about how correlation coefficient deals with outliers. And like the mean value, correlation coefficient is also very sensitive to outliers. So let's see this in the slide now. We can see in the slide 3 graphs are shown. In the first graph, you see a linear pattern. All of the points are actually lining up perfectly on a slope moving towards the upside as it goes towards the right hand side. But if you have an outlier, overall the general pattern remains the same. But if we remove the point having x-axis value of 1 to a value which is not on the line, you would straight away observe that the correlation coefficient value falls. And if this value is far away from the general trend, your correlation coefficient would actually reduce much. So while the general data is still, following the same linear trend, but the presence of the outlier has actually affected the correlation coefficient very much. We would call such an outlier an influential point. And in many analysis, we would be removing this outlier to actually give us the general trend. But we have to be very careful when we remove any data point from the data that we have. And this can work in the other direction as well. When the general trend of data is not actually associated, you can still have a very large correlation coefficient if the outlier is suitably positioned. So we can see now in the bottom half of our slide that the general trend is actually not very associated, but because of the outlier, as it moves away towards the slope we would have if we have a positive correlation, the value of correlation coefficient increases. So again, the general idea here is that we have to be very careful when we are dealing with outliers, because our measure of correlation is sensitive to the presence of outliers, and because of that, if our data has outliers, the measure that we have of correlation, it may be misleading. So as emphasized earlier in an earlier session, it's always a good idea to start by plotting your data and not depend too much on statistical measures, because statistical measures are mathematical abstractions. They may or may not capture the idea that you want. So we have to use our judgment to then understand the statistical measures in that context. Lastly, correlation, just because we have correlation does not mean we have a causal effect. So we've actually covered this before in the session on logical fallacies, when we talked of the fallacy which is known as cum hoc ergo propter hoc fallacy. In English, it means that with this, therefore because of this. So just because two things happen at the same time, we cannot say that one thing is causing the other thing. So because two things are happening at the same time, they may have a very high correlation, but it is not necessary, and it does not follow from this that the two variables have correlation, that either one is causing the other. It may actually be that the variables are correlated, but there is some other lurking variable which is actually causing both of these variables, the increase or the decrease in both of these variables. We also call such a variable as a confounding variable, because we confound the effect of this hidden variable with the effect produced by the variables that we can see. So as an example to illustrate this, please refer to this slide. So we have two amusing examples to illustrate that correlation is not causation. The first example is, amongst elementary school children, feet size and the ability to spell is positively correlated. And the second example is, the number of teachers in a district and the number of failing students are positively correlated. In both these examples, while we can observe a positive correlation in the two variables that we are observing, in both these cases, we have a confounding variable. In the case of elementary school children and the size of their feet and their ability to spell, the confounding variable is the age of the children, which is actually causing their ability to spell to improve. And in the other case, the confounding variable is the population of that district. If you have a higher population, you would have more students, you would also have more teachers. Because you have a higher population, the number of failing students would also increase. So because of that, the real confounding variable is producing the real effect, while we can, if we are not very careful, we can attribute the causality incorrectly to the variables that we are observing. So we must be very careful, especially if we are dealing with an observational study, because to establish causality, it is important that we do controlled experiments. And we'd be studying this when we come to the module of design of experiments of our course. But it is very important that we remember that correlation on its own is not causation. And a quote by Edward Tufte is very apt, and we should mention it here. Edward Tufte says that correlation is not causation, but it sure is a hint. So again, if you have a causal relationship, the physical manifestation of that would be that two variables actually move in sync. But just that the fact that you've observed that two variables are moving in sync, that does not establish causation. To establish causation, you have to do controlled experiments. So with this, we come to the end of the first part of this session, and we would now be talking about regression, which is, if you know that two variables are associated, how do we actually make some predictions? So we need to form a model, a statistical model, and then knowing that a certain value of the independent variable has a certain value, you want to predict what the dependent value would be. So first of all, let me clarify what are the differences between correlation and regression. In correlation, we don't have this notion of an independent variable and a dependent variable. We do not assume that one function is causing the other function. In fact, correlation would be the same if we measure either way. The correlation of x and y is the same as correlation of y and x. But when we are doing regression, we assign one variable as the independent variable, or in other words, we call that the explanatory variable. And we say that we're going to make changes in this variable and we're going to predict what the value of the other variable would be. And that variable is now called the dependent variable or the response variable. So this is the fundamental difference between correlation and regression. Knowing this, now we can move on to understand how regression works. So regression actually comes in many flavors, and it is actually used a lot in industry and abused as well. So we need to be very careful to understand what regression can do and what it cannot do. To understand the basics of regression, we are going to focus on the simplest version of regression, which is known as simple linear regression, in which you are only seeing the relationship between one independent variable and a dependent variable. In general, you can have more than one independent variable, because it may be that the dependent variable actually takes input from many different effects. But for simplicity's sake, we're going to start with just this one independent variable, and we're going to study simple linear regression model. So how do we form this model? The general idea is that we represent the general trend of the scatter plot or the relationship between two variables by drawing a line through these pairs of variables. And this line is actually predicting for us, for a given value of x here is the independent variable, what the value of your dependent variable would be like. Now the question is, how do we actually form this regression line, and what is the interplay between correlation and regression? So to understand this, because you can actually form many different lines through which act as an explanation for the data. But we'd be seeing that we have a single best line, and we define now what is this notion of what is the best line. So to understand that, let's have a look at this slide. We have some observed values, and we want to form a statistical model for that. So what we will do is we will determine a line which is actually a good match for most of the observed values. So we represent y of I as the actual observed value, the actual ith observed value. And when we draw the line through these points, the prediction of the regression line for the same x point, the value of the x variable, the value that you get for the y variable is known as the predicted value. We define as the best fit line as the line which minimizes the residuals, and we define the residuals as the difference from the predicted point and the observed point. And this was actually proposed by a very famous scientist, Gauss, who said that the best line is the line which minimizes the square of errors, or the mean square error. And in this aspect, we have many different notions which actually specify how much errors are there in the regression, and how good a fit is the regression line to the data. So we have something known as the sum of square errors. In this, you have the difference between the actual observed values and the predicted values. So you take this residual and you take the square of this and you sum it up for all the I points that you have. And if you take the average of this, you have the mean square error, and this average is done for a sample. So because of that, you do not divide this by n, but by n minus 2. And we'd be seeing why we are actually dividing it by n minus 2. Also, if we take the under root of MSE, the mean square error, we would have the root mean square error. And the intuitive notion of it is that RMSE, the root mean square error, is just like the standard deviation. Standard deviation क्या measure करता है? वो measure करता है कि mean से कितना दूर आमतौर पे values होंगी. RMSE measure करता है कि आमतौर पे regression line से कितने दूर observed values होंगी. Mean square error is like the variance and RMSE is like the standard deviation. So in general, the intuition behind the discussion now is that you want to find a line which minimizes the error, and we can quantify the error either by the sum of square errors or by the mean square errors, which is the mean of the sum of square errors, and we can also specify the error by the root mean square error. Okay, so now let's talk about how do we actually go about forming this line. So we've already mentioned when we were talking about correlation was that correlation, perfect correlation को हमने ऐसे define किया था कि if one variable is one standard deviation above the mean, if it also produces or it is associated with a corresponding change in the other variable of being one standard deviation above the mean, we would call this perfect correlation. तो इसको हम illustrate करने के लिए एक line draw करते हैं which is known as the SD line. और इस SD line में for every increase of one standard deviation in the x value, you have an increase of one standard deviation in the y value. इस वजह से इस line का जो slope है, that would be the standard deviation of y divided by the standard deviation of x. And that follows from the equation of lines. You must recall from your earlier studies that a line can be specified as y is equal to mx plus c, where m is the slope of the line. So in this case, we actually are going to have a slope of the standard deviation of y divided by the standard deviation of x. So that would be s of y divided by s of x. That would be the slope of your SD line. But we are not always going to have a perfect correlation, and because of that, we are going to often have a line which is not as steep as the SD line. And then how do we actually determine the line that we would be having for our data? So for that, we need to understand how can we go about minimizing your errors. So to understand that, let's have a look at a scatter plot. This is a scatter plot between heights and weight of an individual. Because both of these variables are associated with a single person, we can try to find the correlation and also find a regression model for it. So we see that the scatter plot is diffused across a line that we can imagine which goes through it. But how do we determine this line? So for that, we can find averages for vertical slices. आप सोच सकते हैं कि x axis जो आपका independent variable है, उसको आप divide करते हैं into vertical slices, and for each of that vertical slice you calculate the average for it. So we can imagine, for example, taking values which are close to 72 inches, closer to 72 than it is to 71 or 73 inches. और फिर हम देखें for all the values that are associated with this vertical slice, what is the average value? So this comes out to be 170 pounds. And you can do this for all the vertical slices. And you're going to get a line of averages. We call this a graph of averages. For each vertical slice, you have an average. And the idea is that if you have a line which is the closest match to this, the errors would actually be minimized. This follows from the fact कि mean भी जो होता है in any distribution, जो mean होता है, and we've studied the physical analogy of it. हमने कहा था कि if we imagine a distribution to be made of solid, mean जो होता है उस पे वो balance हो रहा होता है. In other words, the error from the mean is actually the minimum possible that you can have. अगर हम mean को आगे पीछे करें, the arithmetic mean, तो आपकी variance बढ़ जाती है. Minimum variance होता है at the mean. इसी तरह यहाँ because for each vertical slice we have the average. अगर आपने errors को minimize करना है तो your line should be a smooth version of it if all these averages are not perfectly aligned. अगर perfectly aligned है तो that would be your regression line. But if those are not perfectly aligned, your regression line would be a smooth version of the graph of averages. So now let's study the equation of a line as it pertains to the regression line. So for this line, we're assuming a positive correlation and we're talking of simple linear regression. So you have two parameters that need to be defined to specify the line. The first thing is the y-intercept. Yani कि what is the value of y when x is equal to 0? This would be the point जब आपकी line जो है y-axis को intercept करेगी. This is specified by the parameter beta naught. And the other parameter that we need to define is the slope of the line. Slope का मतलब है कि line किस उसकी orientation क्या है. So this parameter is defined by beta 1 and this is defined as the change in y divided by the change in x. For the SD line that we've already covered, this was the standard deviation of y divided by the standard deviation of x. In general, regression line में the slope or beta 1 is actually equal to r multiplied by the standard deviation of y divided by the standard deviation of x. So if you have perfect correlation, your value of r would be 1. In that case, you are actually on the SD line. लेकिन आम तौर पे because correlations are not always going to be 1, your slope is actually going to be less steep than the SD line. How less steep is it? That would be defined by a parameter of beta 1. So another point that we need to emphasize is that beta naught and beta 1 are parameters that correspond to populations. But when we are estimating it, we put a hat on top of beta naught and beta 1 because we are often using samples to estimate population parameters. So uske liye beta naught or beta 1 pe we have a hat. And also we have a hat on top of the predicted value of y because this is a predicted value and we are going to have some error. ये जो error है इसको हम quantify करते हैं by the term E of I, which actually captures all the other variables that we have not actually accounted for in our regression line. So let's now recap our discussion on SD line and the regression line. So please refer to the slide. So the SD line is actually shown in the slide in which the slope is sy over sx. And the regression line is also shown in which the slope is r sy over sx. So for every increase of sx, you have an increase of r sy. So the line of the regression is less steep than the SD line when the value of r is less than 1. Also, an important point to note is that all these lines actually pass through the center point, which is the mean of both x and y. Furthermore, if you have correlation of 0, the y-axis component of the line would actually reduce to 0 because we mentioned that the slope is r sy over sx. If your r is 0, then you have a horizontal line. So a horizontal line actually is not very helpful because you cannot make any predictions from it. So for all values of x, you have the same y value. So that actually tells us that regression is only useful when you have a high correlation. If you have correlation of 0, you cannot predict the dependent variable from the independent variable. Let's now see an example to illustrate how regression works. So we are going to continue the same example. So the same table is shown on the slide. It is containing values of throughput versus round trip time. And we've already calculated the correlation for this. And the correlation coefficient value of that was minus 0.82. And now we are going to determine the regression line for this. So we need to determine beta naught and beta 1. So to determine beta 1, we're going to use the formula R into Sy over Sx. So we know R, it is minus 0.82. We know Sy and Sx because that can be computed from the sample data. We get a value of minus 11.66. From this we can calculate the value of beta naught, because beta naught is equal to y bar minus beta 1 hat multiplied by x bar. If we plug in the values, we get an intercept value of 1471.4. So if we write this down in the form of an equation, we would have y of I hat is equal to 1471.4 minus 11.66 xi. So we can also plot this now, and you can see that you have a graph in which you have negative correlation, and most of the data are actually quite close to this line, and because of that you have a high correlation. So this actually complements the idea of correlation, and with this you can actually predict for a given value of x, the regression line is giving you a prediction. In most of the cases, as you can observe, the error is not great. So this is quite useful when you want to predict. Another important point is regression line actually depends on which variable you are assigning to be the independent variable and which is the dependent variable. Because if you change that, जो हम error minimization कर रहे हैं उसका perspective change हो जाएगा, and because of that you're going to have a different line in most of the cases, except when all the points are aligned at the 45-degree level. In most cases you would have a different line. इस केस में जो एग्जाम्पल अभी आप स्लाइड पे देख रहे हैं उसको हम कहते हैं regression of y on x, because x is the independent variable and y is the dependent variable here. If we do the other regression of x on y, so you can see that on the slide now. Now the line equation has changed. If you see, अब हम predict x को कर रहे हैं and we know the values of y because y is the independent variable. We follow a similar method and we get a value of xi hat is equal to 104.91 minus 0.058 y of I. And if we plot the graph, we would see now at the y-axis we have the values of throughput, and on the x-axis we have the values of the round trip time, and both of these lines are different, as you can clearly see on this slide. You can also see that both of these lines are actually trying to minimize different errors. जब हम best fit की बात कर रहे हैं y on x, आप देख सकते हैं error जो हम minimize कर रहे हैं वो vertical errors यहाँ show किए गए हैं, and when we are minimizing for the other line, when we are doing the best fit for x on y, तो जो errors हैं वो horizontal हैं. So error in both lines are interpreted differently, and because of that we have different lines. So let me now wrap up this lecture by talking of the quality of the fit. So how do we actually determine the quality of the fit? How good is our regression line? तो उसके लिए there are different methods. And all of them actually are based on the residuals that you have. लेकिन जो method हम discuss करेंगे, that is the method of coefficient of determination. ये जो coefficient of determination होता है, it's just the squared value of the correlation coefficient. इसके अलावा we can also talk of residual errors, the SSE, the MSE, the root square mean error. They also have significance. जैसे हम root square mean error की बात करते हैं तो आमतौर पे your average value would miss the predicted value by this much. Lekin because of a shortage of time, we're not going to talk about that. You also have possible errors due to the estimation that you're doing. Iski wajah se we need to have a confidence interval related to a regression line. Lekin we're only going to focus on the coefficient of determination. A coefficient of determination measures how much of the variation in y is actually explained by the regression line. इसको आप ऐसे देख सकते हैं कि total variation जो है वो होगी आपकी जो observed values हैं minus the mean value. So if you take the square of that, so you would have the squares that are shown on the slide. So and अगर हम sum of square errors की बात करें, so that would be the observed value minus the predicted value. You can also talk of the variation explained by regression, and that is the predicted value minus the mean value. And it may not be obvious yet to you, but if you look at this carefully, the sum of squares for the total variation is equal to the sum of square of the error variation and sum of the squares due to regression. In other words, the total variation is composed of variation explained by the regression and variation that is due to error. And we can now define the coefficient of determination, which is specified by r square. It is equal to the variation explained by regression, and we divide it by the total variation. So this would be SSR divided by SST, and because the SSR is equal to SST minus SSE, we can also specify this as 1 minus sum of square errors divided by the sum of square errors due to the total variation. So having talked about the quality of fit, I refer you to your textbook to learn more about confidence intervals of regression and a discussion on the root mean square errors. I'll be wrapping up the lecture now, and we've talked of two very important techniques that we use in statistics. Correlation is a very powerful concept through which we can determine associations. Session, I would talk about regression. Regression is a very powerful modeling tool in which, knowing one independent variable, you can predict the dependent variable. But we must take care that we do not use this regression model where it's not applicable. So it's important to understand the assumptions of regression. One assumption, all error is normally distributed. Another assumption is that you have common variance across all vertical slices. The errors are essentially the same. You call this homoscedasticity. आमतौर पे इस किस्म की assumptions हम लें तब हमारा regression model is valid. But in many cases such assumptions do not hold true. So we have to be very careful, and we have to see the particular case in which we are applying regression and if our technique applies to it. So I'll close this session now. I'll see you next time, inshallah. Assalamu alaikum.